Hello everybody, my name is Askar Khan, your math coach on Wisdom Outlined Coaching, helping you learn. Welcome to the channel. In this lesson, we will learn real numbers and their decimal expansions. We have already learned what real numbers are. We will look into how real numbers can be written in the decimal form and how they can be identified as rational numbers or irrational numbers. And we will also change decimal numbers into fractions. How we do that, we will dive into the lesson. We already learned that real numbers are of two categories. One is rational numbers and the other are irrational numbers. We learnt that in our previous videos. Now, what are rational numbers? Any number that can be written in the form P over Q, where P is an integer and Q is an integer and Q not equal to 0 is a rational number. For example, 3 over 5, negative 8 over 6. All these are rational numbers. We also learned that irrational numbers are numbers that cannot be written in the form P over Q, where P is an integer and Q is an integer and Q not equal to 0. Example of irrational numbers, we saw that square root 2, square root 3, pi, and so on. Now let us understand, how can the rational numbers be represented as decimals, and what can we learn by looking at the decimals of rational numbers? How to identify them as rational numbers just by looking at the decimal expansion. Let's take the rational number 7 divided by 8. Is this a rational number? Of course it is, because 7 is an integer and 8 is an integer, and it is written in the form P over Q, so therefore it is a rational number. Now, in your grade 1 and grade 2, you learned how to divide 7 over 8. And when you divide 7 by 8, what is the quotient that you get? It is 0.875. Now observe, when you divide 7 over 8, you get 0.875 and it stops. That's it. So can I say the decimal of 7 over 8 is terminating, meaning it is stopping? Yes, I can. Let's take another example. The second example. 10 divided by 3. Is this a rational number? Yes, of course it is. And using our grade 1 and grade 2 division, 10 divided by 3, if you do this, you will get the decimal 3.3333, and it goes on. Now, can I ask you, is the decimal terminating? No, it is non-terminating because it's not stopping. It's going on and on and on. So the decimal is non-terminating. Correct? But observe another thing. Fine, it is non-terminating. But is the decimal digits repeating? Yes, the 3 is repeating all the time. So can I say that the decimal expansion of 10 over 3 is non-terminating but repeating? Correct? Great. So let's take another example and try to figure out something else. Let's look at this number, 1 over 7. Is this a rational number? Yes, it is. And if you apply your grade 1 and grade 2 math division, what do you get? 0.14 2857, 142857, and on and on and on. So what do you observe? Is it non-terminating? Yes, it's not stopping, so it's non-terminating. Is it repeating? Do you observe that 142857, 142857, these bunch of digits are repeating. So we can say that it is non-terminating but repeating. Whenever the digits repeat, those digits that repeat are written over with a bar. If 3 is repeating, we can just put a bar on 3, which indicates that it's repeating. So what did we observe over here? A rational number, the decimal expansion terminating. A rational number, decimal expansion non-terminating, repeating. A rational number, decimal expansion non-terminating, repeating. So can I say that the decimal expansion of any rational number will either be terminating or it will be non-terminating, repeating? So there are two conditions. Number one, either the decimal expansion will be terminating or it will be non-terminating but repeating, and or repeating. So just by looking at the decimal expansion, now we will be able to figure out whether the number is rational or not. What about irrational numbers? What about their decimal expansion? Let's take a look. Let's take an example of an irrational number such as square root 2. The decimal expansion of square root 2 is 1.4142135623730, on and on and on and on. Now the question is the decimal expansion terminating? No, it is not. So it is non-terminating. Correct? Yes. Another question. Is the decimal expansion, are there any digits or any pattern that is repeating? No, because look, everything is different. 4, 1, 4, 2, 1, 3, 5, 6, 2, 3, 7, 3, on and on and on. So it's non-terminating, non-repeating. Let's take another example of an irrational number, say pi. The decimal value of pi is 3.14159265389, and on and on and on, some other digits. So is it non-terminating? Yes, because it's just going on and on and on. So it's non-terminating. Is it repeating? No, so it's non-repeating. So what can we conclude about the decimal expansion of irrational numbers? The decimal expansion of irrational numbers are non-terminating, non-repeating. So now we can figure out just by looking at the decimal expansion whether a number is rational or irrational. Excellent going. Let's move ahead. Let's have a quick short quiz to check whether you have understood the concept or not. Classify the following numbers as rational or irrational. Square root of 23. Is it rational or irrational? Square root 23. It's not a perfect square. So it is an irrational number. What about square root 225? Square root of 225 is 15 because 225 is a perfect square. So is it rational? Yes, it's a rational number. What about 0.3796? Rational or irrational? It is a rational number. Why do you say that? Because the decimal expansion is terminating. What about number 4? 7.478478 and on and on and on. Is it terminating? No, it's non-terminating. But is it repeating? Do you observe that 478 is repeating? So it is non-terminating, fine, but it is also repeating. Therefore, what type of a number is it? It's a rational number. What about this? 1.101001 and 1 followed by 3 zeros, 1 followed by 4 zeros. What is it? What do you think it is? Think about it. Is it non-terminating? Yes. Is it repeating? No. So it's an irrational number. Great. So let's move on with further understanding, because now you're able to figure out just by looking at the decimal expansions whether a number is rational or irrational. Now let's understand how to express a rational number in the form P over Q. Let's take an example. Say for example 0.2. Is this a rational number? Yes, because the decimal expansion is terminating. So if it is a rational number, it can be represented in the form P over Q as a fraction, isn't it? So let's see how to do this. Because the decimal is terminating, it's pretty easy. Can I write this as 0.2 over 1? Yes, I can. And since the decimal is terminating, shift the decimal point 1 digit onto your right and add a 0. So this will become 2 over 10. Is it now in the form P over Q, where P is an integer, Q is an integer? So it is a rational number in the form P over Q. Great. Let's try another example. Example number 2. Can you try this? Show that 3.142678 is a rational number. If it is a rational number, express it in the form P over Q. Now, is this a rational number? Of course it is, because the decimal expansion is terminating. Now, because it's a rational number, it can be written in the form P over Q. How do we do that? We will write 3.142678 divide by 1, and then we will shift the decimal points. 1, 2, 3, 4, 5, 6. So we need to add 6 zeros. So our new number looks like 3142678 divided by 1 followed by 6 zeros. So this is in the form P over Q, and we have shown it. This is pretty easy if the decimal expansion is terminating. But what about the decimal expansions that are non-terminating, repeating. Now that's not this simple. Let us see how we do that. Let's try this problem. Show that 0.333, which is equal to 0.3 bar, the same thing is written this way, can be expressed in the form P over Q, where P and Q are integers and Q is not equal to 0. Because the decimal expansion is non-terminating, repeating, let's follow this method. Let x be equal to 0.3333 and so on. Let's label this as 1. Now, how many digits are repeating itself? There's only one digit that is repeating itself. Because there is only one digit that is repeating, we will multiply both sides of the equation with 10. Why are we multiplying with 10? Why not with some other number? Because there's only one digit that is repeating. So we will multiply both sides of the equation with 10. So what will that become now? 10x will be equal to 10 times 0.333 and so on, which is nothing but 10x equals 10 times 0.3 is 3.333 and so on. Let's label this as 2. Now what we will do is 2 minus 1. What is our second equation? It is 10x equals 3.333 and so on. Minus, what is our first equation? X equals 0.333 and so on. So subtract them. 10x minus 1x, 9x is equal to 3. X will be equal to 3 divided by 9. Simplify this. The greatest number that can divide both these numbers is 3. So 3 divided by 3 is 1 and 9 divided by 3 is 3. So have we written 0.33 as a fraction 1 over 3, which is in the form P over Q? Yes. So that's our answer. Let's try this. Show that 1.272727 and so on, which is nothing but 1.27 is repeating. You see that bar over 27. Can be represented in the form P over Q, where P and Q are integers and Q not equal to 0. Fine. Is this a rational number? Of course it is, because it's non-terminating, repeating. That means it can be written in the form P over Q. So let's proceed. Let x be equal to 1.2727 and so on. Let us label this as 1. Now, how many digits are repeating? There are 2 digits that are repeating. Therefore, I will multiply both sides of the equation with 100. Very good. You people are getting smart. So we multiply both sides of the equation with 100. So it will become 100x is equal to 100 times 1.2727 and so on. So this will now look like 100x is equal to, when you multiply 100 with 1.2727, you simply have to shift the decimal points 2 units to the right, and it will be 127.2727 and so on. Let's label this equation as 2. Now 2 minus 1. The equation 2 minus equation 1. What is it? What's our equation 2? 100x is equal to 127.2727 and so on. minus, what's our equation 1? X is equal to 1.2727 and so on. So let's subtract 100x minus 1x, 99x is equal to 127.27 minus 1.27. Definitely this is going to be zeros. So 127 minus 1, it's going to become 126. Therefore, x is now going to be equal to 126 divided by 99. So is this in the form P over Q? It is. So we have written this in the form P over Q. You can also simplify 126 over 99, and if the simplified form of that is going to be 14 over 11, because both these numbers can be divided by 9. So great. So we have represented 1.27 recurring in the form P over Q. Let's look at one more example. Let's try this. Show that 0.2353535. So what's repeating? Only 35 is repeating. You see that bar on it? Can be expressed in the form P over Q, where P and Q are integers and Q not equal to 0. Now, is this a rational number? Of course, it is a rational number because it's non-terminating and repeating. So let x be equal to 0.23535 and so on. Let's label this as equation 1. Now, how many digits are repeating? 2 digits are repeating. So I will multiply both sides of the equation with 100. Excellent. So I multiply both sides of the equation with 100. So it will become 100 times 0.23535 and so on. So what does it look like? 100x is equal to, because I am multiplying by 100, I shift the digits, 2 digits to the other side. So it's now going to be 23.5353 and so on. Let's label this as equation 2. Now what do? We subtract equation 2 minus equation 1. What's our equation 2? 100x is equal to 23.5353 and so on. What's our equation 1? X is equal to 0.23535 and so on. Now subtract 100x minus 1x, 99x is equal to, subtract, this is going to become zeros, and 5 minus 2 is 3. 23 minus 0 is 23. Great. Now let's move ahead. X 99x is going to be equal to 23.3. X is going to be equal to 23.3 over 99. But since there is a decimal in the numerator, let's get rid of it. How? We simply shift the decimal point 1 unit to the right. Because we shifted it to the right, we will add a 0. So our x now is 233 over 990. And that is the representation in the form P over Q of 0.235 recurring. So this is how we represent decimal rational numbers into the form P over Q. That's it for this lesson. Thank you for watching this lesson. I hope you have understood it. If you want math help, you have my number in the front page of the video. You can WhatsApp me for further math classes. Thank you very much. Do share this video with your friends, your teachers, your colleagues, and see you in the next video. Until then, happy learning.